Chapter 15, Quantum Translation, Section 15.2, the particle in the one-dimensional box. The potential energy of the particle is zero inside the one-dimensional box, between 0 and A. The potential energy is infinity outside the box. We have two equations. V is 0 inside the box. V is infinity outside the box when x is less than 0 or greater than A. The Schrödinger equation for the particle inside the box is the same as the equation for a free particle because V is 0 inside the box. Therefore, the Schrödinger equation is negative h bar squared over 2m d squared psi over dx squared is equal to E psi. On the left hand side, we have the kinetic energy operator applied to psi. On the right hand side, we have E psi. The potential energy is 0 inside the box between 0 and A. In section 1, we have learned the general solution of a free particle is this: a linear combination of e to the power of plus ikx and e to the power of negative ikx. A sub plus and A sub minus are just arbitrary constants. Again, we have this solution if x is between 0 and A. That means when the particle is inside the box. This solution is the legitimate solution for a free particle inside the box. The particle can never escape out of the box because of the infinite energy barrier at x equals 0 and x equals A. Therefore, this particle is completely confined. And just because the wave function has to be continuous, well, we know the wave function has to be 0 when x is less than 0. The wave function has to be 0 when x is greater than A. And now we know even at the two boundaries, when x is 0, the wave function must also be 0, just to make sure this wave function is continuous at this point. And the wave function is also 0 when x equals A, because when x is greater than A, well, the wave function must be 0. Therefore, to ensure the wave function is continuous, its value must be 0 when x is 0 or A. Inside the box, the free particle has a wave function like this: a linear combination of e to the power of plus ikx and e to the power of negative ikx. A sub plus and A sub minus are simply arbitrary constants. Outside the box, the wave function equals 0 when x is less than 0 or when x is greater than A. And now, to ensure the wave function is single valued and continuous, we have to have these two conditions. Psi of 0 must be 0, psi of A must also be 0. That means at the two boundaries of the box, the wave function must be equal to 0. These two equations describe the values of the wave function at the two boundaries, and therefore they are called the boundary conditions. We have two boundary conditions, one at 0, the other at A. We will prove the energy of the particle must be quantized to satisfy these two boundary conditions. Now let's look at these boundary conditions. The first one is this: when x is 0, the wave function must be 0. So we just plug in the value of x into the general solution of the wave function. We have this: e to the power of plus ikx, e to the power of negative ikx now become e to the power of plus ik0 and e to the power of negative ik0. So the sum of these two terms should be 0, and because this is simply 1, this is also simply 1, we learn that to satisfy the first boundary condition, A sub plus plus A sub minus should be 0. These two are opposite to each other. Therefore, we can rewrite the wave function here. It's A plus times e to the power of positive ikx minus A plus times e to the power of negative ikx. Now we can see there's a common factor, a plus, so we have this a plus here, and then we have e to the power of ikx minus e to the power of negative ikx. The reason we put 2i here and divided the difference by 2i here is because all this in this pair of parentheses is sine kx. Again, it's just because e to the power of I theta is cosine theta plus I times sine theta. E to the power of negative I theta is cosine theta minus I times sine theta. So sine theta can be expressed as e to the power of I theta minus e to the power of negative I theta over 2i. So I'm just replacing theta with kx. So we have this equation. Again, a plus is simply an arbitrary constant. So we can simply set a to be 2 times I 2 times a plus. To simplify this expression, we have psi of x, the wave function of the particle in the box, to be a times sine kx. It just looks simpler, and a is also an arbitrary constant. Now let's look at the second boundary condition. Psi of a is 0. That means, well, a times sine ka should be 0. So now we have a product here. A times the sine function is 0. So can a be 0? Well, a cannot be 0, because if a is 0, the wave function must be 0. And if the wave function must be 0 inside the box, there's no particle in the first place. So a cannot be 0. Alright, then sine ka has to be 0. Now let's examine this. Sine ka is 0. What kind of values can this ka have? We need to review sine functions. We know sine 0 is 0, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, sine negative 5 pi is also 0. So there are an infinite number of solutions to this equation. As long as ka is equal to n pi, we satisfy this equation, and n has to be an integer. Again, sine n pi is always 0 as long as n is an integer. So we have ka equals n pi. It seems k has to be quantized. K has to be a integer multiple of pi over a. Now to satisfy the two boundary conditions, we have psi equals a times sine kx inside the box. And also, k times a should be n pi, and n must be an integer in this equation. Therefore, the wave function of the particle in the box should be a times n pi x over a. Well, n pi over a is k. So over here, you see ka is n pi. So k is n pi over a. Sine kx is sine n pi x over a. There are a couple caveats with the value of n. So first, n can never be 0, because if n is 0, we're looking at sine 0 inside the box, and psi is then 0. That means the particle disappears. There's a 0 probability of finding the particle inside the box. So number 2, n can be positive or negative, because they are identical in describing the probability distribution of the particle, because in the end, we need to take the squared modulus of psi to get the probability density. So whether it's plus or minus, when we take the squared modulus of psi, it's going to be the same. For convenience, we'll just assume n is a positive integer. Alright, therefore n has to be 1, 2, 3, 4, 5, etc. Again, the wave function of the particle in the box is a times sine n pi x over a. N has to be a positive integer, 1, 2, 3, 4, inside the box. And outside the box, the wave function is 0 due to the infinite energy barrier. Now, the first 4 wave functions are showing in this figure. The mathematical expressions are here. Let's look at the math functions. When a equals 1, the wave function is a times sine pi x over a. When a is 2, it's sine 2 pi x over a. When a is 3, we have sine 3 pi x over a, and then we have 4 pi x over a. Now let's examine sine pi x over a. So we have this x from 0 to a, and therefore we plug in the lower limit and upper limit for x, and pi x over a is going to be between 0 and pi. really we're just plotting sine theta from sine 0 to sine pi. Alright, so this is sine 0, this is sine pi. In the middle we have sine pi over 2. Of course, there's a normalization factor, but this is trivial. We don't worry too much about this. Let's just look at the sine functions. Now let's look at this sine function, sine 2 pi x over a. Again, x is from 0 to a. Plug in the value. When x is 0, this whole thing is 0. When x is a, this whole thing is 2 pi. So we have one entire period from 0 to 2 pi. So over here, this is the entire wave. This is sine 0, and this is sine pi, and this is sine 2 pi. And in between, we have sine pi over 2. Over here, we have sine 3 pi over 2, which is -1. So we have this kind of shape. Now we have sine 3 pi x over a. X is from 0 to a. So really, we're looking at a sine function from 0 to 3 pi. Alright, so sine 0, sine pi, sine 2 pi, sine 3 pi. And then in the middle, we have sine 0.5 pi, sine 1.5 pi, sine 2.5 pi over there. And now we have sine 4 pi x over a with this kind of shape. Over here, x is between 0 and a. So 4 pi x over a is between 0 and 4 pi. So really, we're talking about sine 0, sine pi, sine 2 pi, sine 3 pi, sine 4 pi. And then in the middle, we have pi over 2, we have 3 pi over 2, 5 pi over 2, and 7 pi over 2. So that's why we got this kind of shapes. Again, over here, we have only 1/2 of the wavelengths. Over here, when a equals 2, we have an entire wave. And over here, we have 1.5 of the wavelengths. And over here, when a equals 2, we have 2 wavelengths. The wave function of the particle in the box can be written as a times sine n pi x over a. N is a positive integer, 1, 2, 3, 4. Because remember, n cannot be 0. When n is 0, you simply have sine 0 inside the box. That means psi is always 0 inside the box. There's no particle. Outside the box, of course, psi is 0 due to the infinite energy barrier. Now the 4 wave functions are shown in this figure. When n is 1, 2, 3, 4, let's look at the number of nodes inside the box. Over here, we do not see any nodes, but over here, we have over here there's a node. This corresponds to sine pi. We have a node. And now over here we have 2 nodes. This is sine pi, this is sine 2 pi. And now 3 nodes, sine pi, sine 2 pi, sine 3 pi, 3 nodes. So you can see as the value of n increases, the number of nodes increases. And actually, the number of nodes is simply n minus 1. Actually, we have a similar example in general chemistry. When we look at atomic orbitals, well, the number of nodes is also n minus 1. But in general chemistry, we use n as the principal quantum number for the atomic orbitals. Over here, n is the quantum number for the particle in the box. But still, the number of nodes is just n minus 1. As the number of nodes increases, the energy increases. The same statement is true for atomic orbitals. Now let's look at all those expressions. Those are the first 4 eigenfunctions for the particle in the box. The first one does not have any node inside the box, and this one has a node when x is a over 2. When x is a over 2, 2 pi x over a is pi, so sine pi is 0. Now this wave function has 2 nodes, because if you plug in a over 3 or 2a over 3 here, you get sine pi and sine 2 pi. This function has 3 nodes, because when you plug in a over 4, 2a over 4, and 3a over 4 into this function, we get sine pi, sine 2 pi, and sine 3 pi. So we have 3 nodes when a equals 4. And also, we can look at the graph. No nodes, 1 node, 2 nodes, 1, 2, 3. 3 nodes inside the box. Do not count the boundaries as nodes, okay? We're counting the number of nodes inside the box. Now we can normalize the wave function psi. So that means we can determine the value of a, although it's not very important. We can determine the value of a so that this psi is normalized. That means the total probability of finding such particle between 0 and a should be 100%. Again, the particle cannot escape out of the box. Therefore, the probability of finding this particle between 0 and a is always 100%. That means we have this equation. The integral of the squared modulus of psi times dx is just 1. The squared modulus of psi is the probability density. We are integrating the probability density here. It should be 1 between 0 and a. And this psi is sine n pi x over a, so I'm using the sine function over here. You need to be familiar with trigonometric functions. Sine theta is 1 minus cosine 2 theta and then divided by 2. That's what I'm doing here. You can prove this yourself. And then we can separate this 2. We got 1/2 in this integral. Over here we have 1/2 of this cosine function. And look, there's 2 here. Again, it's because sine theta squared. Alright, if you square a sine theta, it's equal to 1 minus cosine 2 theta divided by 2. Alright. It's just trigonometry. Over here, we can easily integrate this. This is just 1/2 of a. This one a little tricky, but still we can do variable substitution. We can multiply this x by 2n pi over a, and over here we have this divided by 2n pi over a. And we can set phi to be 2n pi x over a. This is just standard variable substitution in integral calculus. And then we have this integral of cosine phi. That's really easy to integrate. We also need to take care of the lower limit and upper limit. So x has a lower limit of 0, upper limit of a, and phi is 2n pi x over a. So we need to plug in the lower limit and upper limit of x in here, so that we see the lower limit of phi is also 0, but the upper limit of phi is 2n pi, because when you put x equals a in here, a and a cancel, the upper limit of phi is 2n pi. So we need to integrate cosine phi from 0 to 2n pi. The integral of this is sine phi. Well, sine 2n pi is 0, sine 0 is 0, so this term is going to be just 0. We have a squared times the length of the box over 2. That should be 1. And therefore, the normalization factor a is the square root of 2 over the box length. The normalization function is this: the square root of 2 over the box length times sine n pi x over a. And x is between 0 and a. Again, the normalized wave function of the particle in the box is the square root of 2 over a times sine n pi x over a. This lowercase a is the side length of the box, or the dimension of the box. N is 1, 2, 3, 4, etc. We can apply the kinetic energy operator to this wave function. Let's do it. Okay, the kinetic energy operator is negative h bar squared over 2m d squared over dx squared. We apply this to this wave function over here. It's slightly complicated because you're taking the second derivative. But if you know the first derivative of sine theta is cosine theta, and the first derivative of cosine theta is negative sine theta, you mostly can solve this problem easily. There's also a chain rule, because when you take the derivatives, you need to copy this n pi over a in front of the derivatives twice, because we're doing the second derivative. That's why you have this n pi over a 2 times, or squared, in front of this negative sine n pi x over a. We can clean up everything. We see this is simply the wave function of the particle, and over here we have h bar squared, n squared, pi squared, 2ma squared. Sounds complicated, but h bar is simply h over 2 pi. So somehow h bar times pi is just h over 2. Over here, h bar squared times pi squared is simply h squared over 4. And therefore, we can clean it up. We get this as the kinetic energy, n squared h squared over 8ma squared. So I'm just using the boson to emphasize this. We'll apply the kinetic energy to the wave function. We get the wave function multiplied by a constant, n squared h squared over 8ma squared. And this is the eigenvalue of psi. When we apply the kinetic energy operator to it, therefore the physical meaning of n squared h squared over 8ma squared is the kinetic energy of the particle. Well, it's also the total energy of this free particle, because the potential energy of a free particle is just 0. Therefore, the energy of a particle inside a one-dimensional box is quantized. The expression is n squared h squared over 8ma squared. N has to be a positive integer, 1, 2, 3, 4, etc. The smallest possible energy of the particle is h squared over 8ma squared when n is 1. Because this is the lowest possible energy, we call that 0 point translational energy. It's just the naming. The lowest possible energy is the 0 point energy. Alright, the second and third lowest energies are 4h squared over 8ma squared and 9h squared over 8ma squared. You simply have n equals 2 in this case, n equals 3 in this case. Now, given the kinetic energy of the particle, we can easily compute its momentum, because the magnitude of the momentum is just mv, and mv is the square root of m squared v squared, which is the square root of 2m times the kinetic energy. So you can see this is equal to this. 2m times the kinetic energy is over here. We know the kinetic energy is n squared h squared over 8ma squared. We plug in everything. We clean up this m and m cancel. 2 over 8 is a quarter, and we take the square root. Now we have the magnitude of the momentum of the particle. It happens to be nh over 2a, very simple expression. And the momentum has to be quantized as well. It has to be a integer multiple of h over 2a. The magnitude of the momentum of the particle can also be determined using the famous de Broglie equation. The momentum is h over lambda. And now we have the lambda. We can see over here, this is 1/2 of lambda, this is 1 lambda. Over here, this way, we see 1.5 lambda, and over here we see 2 lambda. From here to the middle, we have 1 lambda, and from the middle point to the right side, we have another lambda. So it's pretty simple. If you know the wavelength of the wave, the wavelength of this function, the square root of 2 over a sine n pi x over a, is actually 2a over n. So over here, n is 1, so the wavelength is 2a. Well, that makes sense, because we're seeing only 1/2 of the wave, which has a length of a. If the 1/2 of the wave is a, then the entire wave is 2a. Over here, this is just the wavelength. When equals to 2a over 2 is a, so this is just the wavelength. The box length is the wavelength. Over here, we're seeing this box length is equal to 1.5 wavelengths. Therefore, the wavelength is 2/3 of a. Over here, we're looking at 2 wavelengths. 2 wavelengths equals a, and therefore, well, the wavelength is 2a over 4, which is a over 2. So this is one wavelength, a over 2. This is another wavelength, a over 2. So once we have the expression for the wavelengths, we use this de Broglie equation or de Broglie relation to compute the momentum. H over lambda is simply h over 2a over n, and then it's just nh over 2a. So look, when we use de Broglie relation, we have nh over 2a as the momentum. Or we can use this equation, we get nh over 2a. So at least the results are consistent. Larger quantum numbers always means more nodes, shorter wavelengths, higher energy, and therefore higher speed of the particle in the box. So again, from n equals 1, 2, 3, 4, the energy goes up, the momentum goes up, the speed goes up, and also the wavelengths gets shorter, and we have more and more nodes from 1 to 4. Over here, no nodes, 1 node, 2 nodes, 3 nodes. Again, the wave function of the particle in the one-dimensional box is this: the square root of 2 over a times the sine function of n pi x over a. The number of nodes of the wave function is n minus 1. So we can see when a is 1, we have 0 nodes. When a equals 2, we have 1 node. The first 4 wave functions, again, have 0, 1, 2, 3 nodes. When n is 1, 2, 3, 4. Alright, in general, energy increases as the number of nodes increases. A similar example is the atomic orbitals of the hydrogen atom. We learned this in general chemistry. When the principal quantum number a increases, the number of nodes increases, and also it's n-1. The atomic orbital energy also increases. The 1s orbital of hydrogen atom has 0 nodes, and the 2s2p orbitals n equals 2, well, they have 1 node. 3s 3p 3d, they have 2 nodes. 4s 4p 4d 4f, well, they have 3 nodes. Again, the number of nodes is just n-1. You can say this for the particle in the box. You can say this for the atomic orbitals. In general, the energy of the molecular orbitals also increases as the number of nodes increases. For example, the energy of the sigma star orbital with 1 node has higher energy than the sigma orbital with 0 node in the H2 molecule. You can say that for all other molecules.